In this lecture, we discuss on the applications of Bernoulli's equation. As already discussed, Bernoulli's equation is one of the prime equations in fluid mechanics, and the entire fluid dynamics and the following chapters we use Bernoulli's equation frequently wherever we want a relation between the pressure and velocity. So today we focus on the applications and try to understand how the Bernoulli's equation is being used practically also. And let us straight away go to the whiteboard. In the previous class, we derived the Bernoulli's equation. That is P by gamma plus V squared by 2G plus Z is equal to constant. Then if you are applying the Bernoulli's equation between 2 points, then P1 by gamma plus V1 squared by 2G plus Z1 is equal to P2 by gamma plus V2 squared by 2G plus Z2. The assumptions involved in this equation are: number one is fluid is ideal fluid. That means non-viscous. Then basically the second one is flow is irrotational. That means rotation components. Then third one is fluid is incompressible. Rho is equal to constant. Fourth one is flow is steady. So these are the flow assumptions involved in the Bernoulli's equation. But with a little modification, the Bernoulli's equation can be applied for real fluids also. Therefore, Bernoulli's equation applicable to real fluids P1 by gamma plus V1 squared by 2G plus Z1 is equal to P2 by gamma plus V2 squared by 2G plus Z2 plus head loss. This term extra will come in case of the real fluids. So this is the total energy at section 1, total energy at section 2 plus head loss. So this is the equation which we use for real fluids. Then coming to the applications of Bernoulli's equation. If we take number one is Venturi meter, number two is orifice meter, number three is Pitot tube. These are the three we are having in our curriculum. So let me start first straight away. What is this Venturi meter? Venturi meter is a device. Venturi meter is a device used for measurement of discharge or rate of flow in pipes. Orifice meter also serves the same purpose, whereas pitot tube is used to measure the velocity of flow in pipes and open channels. So these are the purposes for which these three devices are used. How the Bernoulli's principle, Bernoulli's equation is used in this, that we will take it up. Now let me take straight away the first one, Venturi meter. Already I mentioned Venturi meter is a device used for measurement of rate of flow. This is also called as or discharge. What is the principle of Venturi meter? Principle is what? What we do is by reducing the cross sectional area of the flow passage, we reduce the cross sectional area of the flow passage. A pressure difference is created. A pressure difference is created, and measurement of this pressure difference and measurement of this pressure difference enables determination of discharge. Here important points are: first thing is reducing cross sectional area of the flow passage. Then what happens? Pressure difference is created. Then next what to do? Measurement of this pressure difference, and that enables determination of discharge. So how, what are the various components of venturimeter? The components of venturimeter are: number one, convergent cone; number two, throat; number three, divergent cone. These are the main three components in this. The convergent cone is such that the angle of convergence will be approximately 20 degrees. It may vary from 21 degrees plus or minus 1 degree. And throat is such that its length is equal to 2.7 into d minus d, where basically d is the diameter of the pipe and small d is the diameter of the throat actually. So this is the basically here at the throat length actually. This is the length of the throat. This is, sorry, this is length of convergent cone, where capital D is diameter of dia of pipe and D is dia of throat. And divergent cone is again the angle is around basically 5 to 6 degrees. This will be approximately divergent cone. Throat is generally it will be 1/3 to 3/4 of inlet dia throat diameter. And basically some of the people will keep half also, half dia of inlet. It all depends. So now I will draw the figure and show you what it looks like. For example, if you say it, this is the convergent cone. This is how the convergent cone looks like. Then a small portion throat. Then divergent portion is longer. Divergent portion will be longer. So this is the inlet. This is the outlet. So this is finally how the Venturi meter looks like. If you see, this is the convergent cone, throat, and divergent cone, right? And now it is connected in the main pipeline. The inlet diameter is equal to the diameter of the pipe. And similarly, the outlet diameter is equal to the diameter of the pipe. Here and here, the diameters at this place and at the outlet are same actually. Only thing is this angle is around 21 degrees and this angle is 5 degrees. That should you should remember. Whereas this length is equal to 2.7 times d minus d, where this is the inlet, or otherwise I can write better d1 minus d2, where d1 is this and d2 is throat. Throat diameter is d2, right? This is what the basic thing is. So the flow enters now here and the flow leaves like this. So this portion is called as the convergent cone, and this is throat, and this is divergent cone. The length of the divergent cone is more than the length of the convergent cone. That itself the angle speaks about. Now what we are doing, connecting actually the inlet and the throat by a differential manometer. We are connecting the inlet and the throat by a differential manometer. And this is the differential manometer reading. And this reading is equal to some h. Actually, what happens is here, if you take it, the diameter is more, area is more. So when area is more, according to continuity equation, the discharge at all the places is same. So if you take inlet, D1 is greater than D2. So when D1 is greater than D2 and A1 is greater than A2. So naturally, when it is A1 is greater than A2. So if you take it, naturally velocity, if you take it, velocity V1 is less than V2, because continuity equation is what, A1 V1 is equal to A2 V2. So as area is increasing, right, here to here A1 is greater than A2, so V1 should be less than V2. That's what from continuity equation. Then naturally, what is the relation between the Bernoulli's equation, pressure and velocity? So here if you take it, initial stage, actually as the velocity is more, that means velocity head is more. When the velocity head is more, pressure will be less at the throat, whereas at the inlet the velocity is less, velocity head is less, so pressure will be more. As pressure is more on this side, the differential manometer, the liquid is pushed down, whereas on the other side the liquid is pushed up. So here you remember, as V1 is less than V2, pressure, if you take it, P1 is greater than P2. Because of P1 is greater than P2, this is how the liquid is being pushed actually. Now let us, this is some manometric liquid. So now straight away let us go to the derivation part quickly. So let D1 is the diameter of the inlet and D2 be the diameter of inlet and throat. First one. Next, A1 is the area of the inlet, A2 is the area of throat. Right. Next, actually, let V1 be the velocity at the inlet and V2 be the velocity at the inlet and throat. Then let P1 is the pressure at the inlet and P2 is the pressure at the throat actually. So that is the next one. So these are all the basic things. Now assuming that the fluid is incompressible and there is no loss of energy between sections 1 and 2, that means the section 1 means actually here for us it is inlet and section 2 means actually throat. So there is no loss of energy between the section 1 and section 2. So when there is no loss of energy between section 1 and section 2, straight away we apply the Bernoulli's equation. The Bernoulli's equation is P1 by gamma plus V1 square by 2G plus Z1 is equal to P2 by gamma plus V2 square by 2G plus Z2. So as basically the venturimeter is connected in a horizontal pipe, the venturimeter is connected in a horizontal pipe, then naturally Z1 is equal to Z2. Therefore, P1 by gamma plus V1 squared by 2G is equal to P2 by gamma plus V2 squared by 2G. Then rearranging the terms, P1 by gamma minus P2 by gamma is equal to V2 squared by 2G minus V1 squared by 2G. Right? What is this P1 by gamma minus P2 by gamma? This is nothing but the pressure head difference. Pressure head difference. Pressure head difference between the inlet, one means inlet, two means throat, and this is represented by H. Now H is equal to V2 squared by 2G minus V1 squared by 2G. Right. Now according to continuity equation, if I write the continuity equation, A1 V1 is equal to A2 V2. And A1 V1 is equal to A2 V2 and it is nothing but equal to Q theoretical. What do you mean with TH means theoretical? Then if I want V1 is equal to Q theoretical divided by A1. V2 is equal to Q theoretical by A2. So therefore H is equal to, right, V2 square. V2 square means QTH square by A2 square into 1 by 2g minus qth square by a1 square into 1 by 2g, because it is v2 squared by 2g minus n. So if I take common qth square by 2g into 1 by a2 square minus 1 by a1 square is equal to qth square by 2g into a1 square minus a2 square by a1 square a2 square, or 2gh is equal to qth square into a1 square minus a2 square by a1 square a2 square. Now if you take it, what is qth square? If I see, it is a1 square a2 square 2gh divided by a1 square a1 square minus a2 square is equal to qth square, or qth is equal to a1 a2 root 2gh divided by square root of a1 square minus a2 square, or qth is equal to a1 a2 root 2g divided by square root of a1 square minus a2 square into root h. The ratio of actual discharge to theoretical discharge is coefficient of discharge. Mathematically, we can write CD is equal to Q actual by Q theoretical. Therefore, Q actual is equal to Q actual is equal to CD into QTH theoretical. It is equal to CD into A1 A2 root 2G divided by square root of A1 square minus A2 square into root H. So the equation for actual discharge is equal to the above one CD. Once again, A1, A2 root 2G divided by square root of A1 square minus A2 square into root H. So this is the equation of Venturi meter. And the CD value for Venturi meter approximately will be 0.98. As the CD value is less than 1, kindly remember that the actual discharge will be always less than the theoretical discharge. So this is the first point. So A1 is known, A2 is known, G is known, CD is known. So all this you can calculate easily. This portion can be calculated easily. But how to calculate this portion? So that portion is nothing but H is equal to, P1 by gamma minus P2 by gamma is equal to, directly you can see from the manometer reading actually, that is whatever the deflection, it is X into SM manometric fluid by S1 flowing fluid into 1. So using this, we can calculate here SM is the manometric fluid, S1 is here, the flowing fluid, 1 is this, and deflection in the manometer is this. Suppose if you take mercury, then match naturally for mercury, SM is equal to 13.6. And flowing fluid, if they don't give anything natural, it will be water, or otherwise if they give specific gravity, we can calculate it. So by using this, we can find out this by using this device, what is the discharge in the case of pipes. We can find out using Venturi meters exactly. Now in order to determine the discharge in the pipes flow, whether it is water pipelines or whether it is oil pipelines, everywhere the Venturi meters are being fixed in the pipeline wherever we want to really determine the rate of flow. So here we will stop in this class actually and take up the next device, which we call it as the pitot tube, in the next class.
Like, share, and subscribe. Hit the bell icon for more updates.